Hi, let's continue with this formulation of the equations to draw or represent the three-dimensional uh, principal stresses on a Mohr's circle. So in this case, we ended up with the equations of equilibrium for the inclined plane. One detail I notice now is that this sign here is incorrect, so it should be positive. So this, please take into account this. We'll try to put a note in the previous video just to let you know that it wasn't correct. Anyway, what we're going to do now is to try to use or arrange these equations in a way that are better suited to make our or draw our conclusions. So we can do some simplifications here, and that's what we're going to make kind of as part of this video right now. So we understood that we had from our initial plane oriented in this way, we basically found or constructed another plane oriented in the direction that we are now calling normal, and other direction here that we can call this S. Basically, I call them also X prime and Y prime. We found out, thanks to the formulation of the equilibrium equations, that I know how to calculate, or I know the value of sigma NN in function of the previous stresses located in the original plane configuration. And we found also this stress tensor here, NS. However, there is a third stress, a normal stress that we need to calculate here to make this new orientation of the plane fully described, and that is a kind of this normal stress aligned with the S axis or Y prime axis, and I can call it SS. To make the nomenclature or the notation a little bit easier, I will call this normal vector as sigma X prime and this other normal vector as sigma Y prime. Let's remember that because of thanks to the reciprocity of shear stresses, I have also this stress here. It's going to be Sn. It's going to be similar to this one. Okay, so to calculate the other stress or the stress aligned perpendicularly to the normal stress that we already calculated and is represented in equation 1. One thing that I could do is that say, okay, I know that this is the result for the normal stress in the n direction. If I want to know what's the normal stress in the y prime direction, this one here, then it means that I could take this representation here and let's say describe it at a different angle. We know that from our original kind of proposition of the problem, we had that this vector form a theta angle with respect to the x-axis. Then I know that the y prime vector forms a theta plus pi divided by 2 angle. Then if I change here in each one of these terms the angle where this is represented, then I could obtain not the new, or not the new, the perpendicular normal vector to this normal one here, or to sigma NN. Let's see. If I want to substitute this angle instead of the angle theta to find the sigma y prime, one of the things I would need to do is try to simplify my equations. I know that the cosine of sigma plus pi half is equal to minus sine of sigma. And I know also the sine of this new angle, trigonometrical identity, is equal to the cosine of theta. Right. By doing this, I can simplify my equations. I can always write it in this fashion, but if I write it like this, I will get some similitudes that will allow me to compare things. Okay, let's start. Sigma y prime is going to be equal to first term, this one here, sigma x times cosine square of sigma, and cosine square of, not sigma, cosine square of theta. And we know that instead of theta, I have to put this theta plus pi half. It means that's going to be end up multiplying 2 times this sine of theta. That's going to be sigma xx times sine squared of theta. Plus, I have this other term here. So sine square of theta plus pi divided by 2. So that transforms into sigma yy cosine square of theta minus 2 times the shear stress xy times sigma, this one here, sorry, sine theta plus pi half, and that changes to cosine theta times cosine of theta plus pi half, and that's equal to minus sine of theta. So I will write here sine of theta, but I would change this to positive. We'll call this equation 3, which is going to be how to calculate the other stress represented in the oriented or differently oriented plane. Good. Now let's keep simplifying these things, these equations. Let's see. Yes. Another simplification we can do here using, again, identities is as follows. If I consider that the cosine square of theta is equal to this, cos plus cosine 2 theta divided by 2. I consider that sine square of theta is equal to 1 minus cosine 2 theta divided by 2. And I consider that the sine of theta times cosine of theta equals to sine 2 theta divided by 2. Then I could transform, or I could utilize that new information into equations 1 and 2. And why not in equations 3 is needed. We are going to limit this application or this insertion in equations 1 and 2. Right. Let's start with equation 1. Here we have it again. We have sigma, I'm going to write it again with the new sigma x prime is going to be equal to sigma x cosine square of theta, and cosine square of theta is going to be 1 plus cosine of 2 theta divided by 2 plus sigma y, yes, times sine square of theta, and sine square of theta is going to be 1 minus cosine 2 theta divided by 2. Then minus 2 times the shear stress sine times cosine, minus 2 times tau xy sine of theta, cosine of theta, that is, or I can write it as sine of 2 theta divided by 2. Yeah, the first thing that I see that can cancel out are these 2 here, and I could expand a little bit these parentheses that I find here, or I have here. I'm going to write them. Sigma x prime equals to sigma x divided by 2 plus, yes, can I do this? Yes, I can do this. Yes, so sigma x times cosine 2 plus kind of just opening up this parenthesis, my y cosine of 2 theta divided by 2 minus tau xy sine of 2 theta. Yeah, keep working on this. So I'm going to start grouping terms, and the first one is going to be this tau xy x prime, or sigma xy, sorry. It's going to be equal to sigma x plus sigma y divided by 2 plus sigma x plus sigma, or minus in this case, sorry about that, minus sigma 1 divided by 2 and multiplied by cosine of 2 theta. Then minus tau xy sine of 2 theta. Great. I will, if we can leave it at this stage, and this one I will call it equation 4. Let's do this. Let's do the same with to the shear stress equation here. I will have that in another color. Tau ns. Reduce this size. Yes. Equals to, first term is what it is, this one here. Yeah. Shear stress times the subtraction of the square of the cosine and sine. So tau xy minus cosine, yeah, cosine square of theta, that's how to write it beautifully. Yeah, kind of something like this, cosine. Yes, minus 1 minus the cosine of 2 theta divided by 2. What's next? Next is this one here. 2 normal stresses, sine, cosine. And it is max plus, yeah. Plus sigma y minus sigma x. Cosine, sine times cosine and of theta, and then that's sine of 2 theta divided by 2. Yeah. I'm going to expand this a little bit. So it's a tau xy times 1/2 plus cosine 2 theta as 2 minus 1/2 plus cosine 2 theta divided by 2 plus, can I leave? Yeah, I believe we should leave this one here like this, sigma y minus sigma x here, sine 2 theta divided by 2. Yes. Then I know that I could cancel out these ones and this one, and this is added to this 2 theta plus tau xy cosine of 2 theta. And I will call this equation number 5. Now we have the representation in the form we need to make a kind of a simpler operations. To continue finding out how to construct the Mohr circle for 3-dimensional stresses. In our next video, we will talk about the principal stresses in this planar representation. So how to come from this equation 4 and equation 5 to calculate the principal stresses. Also, we will mention how to calculate the maximum shear stress found there. And from those relations, we will be able to draw the Mohr's circle for the two-dimensional case. Thanks for watching.